Hello. In this video, I'm going to describe the operations that can be performed between two NumPy arrays. So these are the same operations that we already learned in the context of scalars. You can add two scalars or multiply two scalars, and it turns out that you can do the same with NumPy arrays. But you do have to be a little bit careful when those arrays are not of the same size. So we'll go over the different cases that come up. Before we get started, I want to recall this slide from the presentation on the Standard Libraries math package, where I laid out all of the functionality that is available from that package. I want to stress now that NumPy is replacing all of this. So we will no longer need the math package. We're just going to get all of our mathematical needs from NumPy. And you don't have to memorize new names for all of this stuff. In fact, NumPy just gave everything the same name as in the math package, with a few exceptions. So instead of calling this a cosine, in NumPy it's called arc cosine, and the same for arcsine, arctangent, and arctangent 2. And the other difference is with the power of function x to the y, instead of POW, in NumPy we spell it out, power. But aside from that, everything else is the same. You'll remember this table of operations that apply to scalars. We had addition, subtraction, multiplication, division, exponentiation, quotient, and modulus. Well, this turns out to be the exact same set of operations that applies to NumPy arrays. I'm going to invent here a new symbol that's going to be this circle with a cross in it. And that's going to stand for any one of these. That's just to simplify the presentation. All right, suppose you have two arrays, we'll call them A and B, and you want to combine them with an operation. So perhaps you want to add them, or maybe you want to multiply them, or maybe you want to take A to the bth power. What is NumPy going to do in each of these scenarios? Well, there are three cases. Two of them are easy and one is less easy. Let's take first an easy case, that the two arrays involved in the operation are of the same shape. And I'll remind you here that this symbol stands for any of our operations. Okay, in this case, NumPy will apply the operation element-wise. And what that means is that it's going to take corresponding elements in the two arrays, so the 0, 0th with the 0, 0th, and it's going to do the operation on those two scalars, so 12 minus 2, and that's going to be the result in the 0, 0th position of the result. Then we could do the 0 first, 3 plus 5, that gives us 8, and so forth. So you see, we'll end up in this case with an array that's of the same shape as the two arrays that were involved in the operation. Okay, let's go to the second easy case, an array of any shape or size with a scalar. In this case, again, it's going to be element-wise. So it's going to take the scalar and it's going to apply it, the operation, to each element in the array. So it's going to do the first element is a 12, plus 5, it will get a 17, then 3 plus 5, it will get an 8, and so forth. So again, you see, we'll end up with an array that is of the same shape as the array that was involved in the operation. The third case is a little bit more tricky. So in this case, you have two arrays, but they're of different shapes. And in this case, NumPy is going to apply certain rules that are called broadcasting, and that we'll see next. NumPy will broadcast whenever it has to perform an operation between two arrays of different shape. So let's say you have an array that has 3 columns, and it has a bunch of rows, and you want to perform an operation with another array that has just 3 elements in it. So NumPy will look at this and say, well, these two have different shapes, so we have to broadcast first before doing the operation, and the broadcast will result in two arrays that have the same shape, and then we can do the operation element-wise. So it will consult its rules, and it will find that in this case, it has to take the elements of this array and copy them once for every row in the other array. And so now it has two arrays of the same shape, and it performs the operation element-wise. Now, the general rule for broadcasting in NumPy is a little bit complicated. Keep in mind that NumPy arrays can be of any dimension, not just one or two. They can be 3, 4, 5, 6 dimensional. And the rule has to work no matter how many dimensions and what shape the two arrays have. So on the other hand, most of the arrays that we use in engineering and science are of array of dimension 1 or 2. Yes, sometimes we need 3D cubes of data, but very seldom do we need 4 or 5. So instead of describing the general rule here, what I'll do is just describe how it applies to arrays of dimension 1 and 2. That is just arrays, linear arrays, and matrices. The simplest case I'm not even showing here is when both arrays are one-dimensional. And in that situation, there is no broadcasting. So the two arrays simply have to be of the same size, and then the operation is done element-wise. And if they're not of the same size, then the operation is invalid. So broadcasting only really begins when at least one of the two arrays is two-dimensional. And the easiest case of that would be when one is two-dimensional and one is one-dimensional. So that's the one I show here. And it doesn't matter which order they come in. The order doesn't matter. So here we have a two-dimensional array or a matrix, and that's indicated by the square brackets, and a one-dimensional array, and that's indicated by the parentheses. The condition for the broadcasting to be done here is that the number of elements in B, so that's len of B, must be the same as the number of columns in A, so the 1th element of the shape tuple of A. In that situation, it will just do the same thing as we saw in the previous slide, take the elements of B and copy them, make a copy for each row in A. Now, the other two cases are when both of the arrays are two-dimensional. And in that case, at least one of them must have the size of its dimension be 1. So it has to be either a row matrix or a column matrix. Both of them cannot be rectangular matrices. So if it's a row matrix, then the situation is the same as this one. We just take the values of that row matrix and copy it for every row in A, and then we have two things of the same size, and we perform the operation element-wise. And if it's a column matrix, then we do the same, but we copy for each column in the other one, and then perform the operation. So let's see this in code. This is the same code as was shown in the previous slide. So let's start with the 2D operation 1D case. Now we can confirm that A is two-dimensional by looking at its ndim attribute, and that's 2, while B is one-dimensional. A's shape is 2 by 3, and B's shape it just has 3 elements in it. So what happens now if I do A plus B? Well, it's going to copy B and make 2 rows so that it's the same shape as A, and then it does the operation element-wise. So in this case, we'll get 0 plus 1, 0 plus 2, and 0 plus 3 in the first row, and then 1 plus 1, 1 plus 2, and 1 plus 3 in the second row. So there you have it. Now in the case that one of the arrays is a row matrix, that's this case, and I've made B a row matrix by using double brackets. So this is a matrix with just a single row in it. Now when I do A plus B, I get the exact same thing. So as I said before, these two cases are equivalent. However, let's check this. What if I were to remove one element from B? Now the broadcast becomes invalid because the condition is not met. So that does not work. The third case is when one of the two is a 2D column matrix. And in that case, the number of rows has to be the same in both matrices. In this case, 2. So this is a column matrix because it has 2 rows and each row has only one element in it. So when I do the sum here, it's going to add the column 1, 2 to the first column, which is 0, 1, and it's going to get 1, 3. And the same for the second column and the same for the third column. So we get 3 columns that are 1, 3. Again, if I violate the condition, the broadcasting does not work. Let's see what would happen if this were exponentiation. Well, it's the exact same thing. I have to close this bracket, and I get 0 to the 1 and 1 to the 2. That's 0 and 1, and I get that repeated for 3 columns. Okay, let's look at a final example. In this problem, we have a cell phone tower that is located with respect to a 3D coordinate frame at position xt, yt, zt. And then we also have a bunch of cell phones, and they're out and about in the world. There's cell phone 1, 2, 3, 4, etc. up to n. So there are n cell phones. This is the ith one. And each cell phone has a position, which is xi, yi, zi. And so we can calculate the distance from the cell phone tower to each cell phone, and we'll call that di. And we can calculate it using the Euclidean formula. So our goal with this problem is to find which of the cell phones is closest to the cell phone tower. All right, so here I'm importing NumPy and I'm importing the data, the position of the tower and the position of the phones. And you can see that I'm getting these from text files using NumPy's load text function. So we'll learn more about that later. For now, we're just going to consider that we have the data. The position of the tower is a 1D array with 3 elements, 2, 23, 45, and 10. And those are the x, y, and z positions of the tower. Let's look at the phones. Okay, we have many, many phones. Let's see how many. If I look at the shape of this, I can see that it has 200 rows. So we have 200 phones and 3 columns. So the x, y, and z position of each of the phones. And here is the formula that we want to compute. All right, so what do we have? We have the position of the tower, and that is an array with 3 elements in it. And we have the position of the phones, and this is a matrix, a tall matrix with 3 columns in it. Okay. And if we look at this formula, we see that for the ith phone, this phone here, we're going to have to subtract its x position from the x position of the tower, its y position from the y position of the tower, and its z position from the z position of the tower. So this is an operation that is really well tailored for NumPy's broadcasting, because that's exactly what it will do if we say position of the tower minus position of the phones. Okay, so it will take the position of the tower, copy it 200 times so that we get 2 equal-sized arrays, and then do the subtraction element-wise. And here we have it. So here, this entry is xi minus xt, this is a yi minus yt, and this is a zi minus zt. So the next thing we have to do is take each of these elements and square them. And that's also something that NumPy is good at, because if I say the square of this it's just going to do that element-wise, which is exactly what we want. So now this is xi minus xt squared, yi minus yt squared, and zi minus zt squared. Now what's the next thing we want to do? We want to add these three things for each phone. So we want to do a summation horizontally. And we'll get something then when we do the summation horizontally that will be a tall column vector or an array, a 1D array. Let's do that. So now we do the sum, np.sum, and we want to make sure that we specify that we're doing it horizontally. So the axis we set equal to 1, and that gives us a 1D array. Let's make sure that it has the right shape. Yes, it's a 1D array with 200 entries in it. Very good. So now all that remains is to take the square root. And again, we want to do this element-wise for each of the cell phones. So that is exactly what a NumPy will do. np.square root. I get now this, we'll just call this D. And this is still a 1D array with 200 entries. Great. Well, what we really want is to find the cell phone that is closest to the cell tower. So we want to find which amongst all of these numbers is the smallest. And that is something we can do with np.min. And we pass in D. And it tells us that the closest cell phone to the cell tower is 173 distance units away. But what we really want is we want to identify that cell phone. So we can use argmin. And argmin is going to give me what is the index in D of the smallest number. So that's 74. It's telling us that the 74th cell phone, or the cell phone in the 74th position, is the one that is closest. So we could call this index. And next what we might want to do is find the position of that phone. So position of the phone, and we want to extract from that the 74th row. So now to do that, we would be indexing the position phones array, and that's going to be the topic of our next video. So I'll see you then. Bye.